It gives me great pleasure to announce the next speaker for the conference. Many of you know him by many names, which I probably don't know. But one thing I will do want to share with you is A, he's a good friend. And B, he's been putting on a great conference over the last couple of years. Everyone, please welcome Jared up on stage.
When you're working on a project, there are many moving parts. And each part of this data pipeline has its own considerations. And those considerations become more difficult when you're working with medium data. Medium data is harder to handle than people think it is. It's big enough that it doesn't fit into memory, but small enough that you shouldn't be using Google scale tools. So you need to figure out how you're going to work with it. It takes a little bit of thought. So we're going to discuss some of those tools. And as our motivating example for today, we are going to be talking about taxis. Yes, that's Cash Cab. And yes, I was on it very, very early as one of the first contestants. The New York City Taxi Data is publicly available on AWS for anyone to get and examine. In fact, it's been used a lot for medium data case studies. Our goal for today has a few steps in it. First, we are going to pull the data from S3, but we only want to pull the data if it has changed, because we don't want to pay for that egress fee. Then we are going to keep data only from certain geographic areas of our data set. And then we want to only keep rides which are represented by a row where all the rides for that given day were over some threshold, say $6 million. So if all the rides across all taxis for a given day was over $6 million, keep the rides for those days and not other days. Then we want to load our cleaned up, ready to go data set into a database. So first up, we have to go get the data. And we can do that using the aws.s3 package using the save object function. We're going to get this object, which is in our case a file, from that bucket and save it to this file locally on disk. And this brings it down. We can read in the dataset just a few columns using fread, take a sample using slice sample, then convert it into an SF object so that we can plot it with leaflet. And we very quickly see there are a bunch of taxi pickups in the middle of the ocean near Africa. We probably want to remove those from our dataset. Notice for a moment though, instead of using the add points function from leaflet, I'm using add GL points from leafgl because it uses WebGL, so it can plot much quicker and it can plot more points than the standard function can. It's a nice add-on that makes life really, really good. So now we have our data, we want to geofilter it. And there are a few strategies we can take. We can load it up into PostGIS right from the get-go and do a spatial query, but that's our end goal, and the data's not ready for that yet. So we could read all the data into memory, convert it into an SF object, and filter out the rows. But we can't be so certain that the data will fit into memory. So we can split this one big file into multiple files, then read and filter each file individually. So that's the strategy I want to go with. I want to split the files. I wrote a function that first deletes any files in the destination folder, saves the header row to be used later, and then uses process X, which we are going to use a lot, to call the bash command split. We call split, we give it a bunch of extra information, how we want the data split up, and then we keep track of all these files we generated. When we run this command, and we take a look at the output directory, we have 319 files plus a header file. So our data is all split up and we could operate over that. In order to do the geofiltering, we first need a map of our desired area. Luckily, that is freely available online and we can read it straight from the URL, which is hosted by ArcGIS, into read SF. And we are going to use this map to keep just some records. We check out the map to see we have each borough of New York City, and we are just going to focus on Manhattan just to make the problem a little bit quicker for today. Also, please note that this map used exactly 4 colors, and according to the 4-color theorem, you can plot any map with just 4 colors, and I think we just proved it with this one simple example. So now it's time to do our spatial filter, and we're going to do this for each of our hundreds of files, so I wrote a function to do that. First, it reads in the header because not all of our split files have headers. Then we use fread for its speed to read in this one file, convert it to a tibble because it's easier for me to work with, convert that into an SF object and set the lat long. Then we use stfilter. stfilter is like a spatial join, but it's only going to keep the columns from the first table, and it's going to reduce the rows based on which points in the first table fall into the polygons of the second table. After we have filtered down our data, notice this is all just one long pipeline, we then convert our geometry object away from well-known text, the way it's stored, into an EWKB. That is a special type of well-known binary, because we can save that in the CSV and load that into PostGIS very nicely. And we set hex equals true, so it comes across as text instead of raw. And then we use fwrite to write this out to a file. And we do that for each file individually, and we mix very nicely data table, dplyr, and SF. We check, before we can apply the function actually, we have to create a mapping of all of our input files, this raw files, and the corresponding output file. That way we can iterate over this data frame and do this one file at a time. We then delete any files that already exist in our output directory and use walk to iterate over this data frame of file names, calling remove points on each file individually. Once we accomplish this, we read in one data set to see what it looks like. We have all the columns we expect, and our geometry column, the last one, is stored as a character because it is a well-known binary, not a raw standard geometry column. With our data filtered geographically, we can now filter based on an aggregation. We want to only keep the rides from days where the daily total was above a threshold. So you can no longer do this one file at a time because you don't know which rows are split into which file. I need to be able to look at the entire data set, and a great tool for that is Arrow. This will allow me to operate on the entire data set without pulling it all into memory while still using a dplyr syntax. This is going to be very, very helpful for us. Now, installing Arrow, even though it's on CRAN, can be a little difficult, especially on Linux, especially in an air-gapped environment. So, luckily, there is this GitHub content which has a function called install Arrow, which will install the Arrow system libraries for you to make it a little bit easier to have the package going in R. To do this step, I wrote another function so it's easy to apply because there are multiple steps in this process. First, we use open dataset to open the entire data. We are not reading it all into memory, but we are making it available to us. And that's the nice thing. It is not all in memory. It is just being made available to us. And that's very important. We then compute a group by summarization. We group by date, we summarize by summing up the total fare, and then we filter out to make sure the fares were over a certain threshold. Now this has not been computed. We've just constructed the query. We will then use this query in a semi-join, which is a filtering join, that will only keep records of our main data set, which have a date corresponding to this filtered out dates. And then we write this result out to a file. Only parts of the data ever make it into memory, which is really, really awesome. So then we call this function and we check it out, and it produced one file. We could have written multiple files, but I want just one for our next step, which is loading to the database. This is our ultimate goal of getting it in here, and for my purposes, one file will be easier. Dealing with databases can be a bit tricky sometimes. So instead of installing the database directly, I am going to use Docker. I'm going to use this to hold the database. This way I can't screw up other databases. Rather than build my own Docker container, I'm going to use an existing one, Cartoza PostGIS, and I will use Docker Compose for spinning it up. I'm using a volume to store the database data, that way it survives reboots. There's also a nice feature that any SQL files I put into a certain volume will be ran the first time the container is spun up. I also set certain environment variables like setting a really secure password such as Docker, and I make sure there are extensions such as PostGIS and HStore and some other ones. And I declare the port to be 5436 because I have multiple of these containers going on for all my projects and they can't all use the same port. That SQL file that creates a table has a regular create statement with a bunch of columns, each with different types, including our geometry column with constraints to make sure it is a point, not a polygon, not a line string, but a point. I don't set any indexes because I'll do that later after I load the data. To spin up the container, I use process X from inside of R, and I call the bash command docker compose. I tell it which docker compose file to use because I have multiples. I tell it up, and -d means detach it. This way it doesn't clog up my terminal. With our database running, we can finally copy from the CSV into that table. But we are not going to use R to do this because that whole CSV might not fit into memory. Instead, we will use psql, a command line tool, which reads straight from a CSV into the database. And I need to provide it a set of SQL instructions. This file starts with begin and ends with commit. And that means that all these steps are part of a transaction. If any one step fails, it will undo all the steps. And that's really important. It's a really great way of making sure you don't screw up massively. Always use a transaction. First, we drop the indexes because it'll be quicker to delete and bulk load into the database without indexes. We delete all the rows in the current table that we care about because we're just doing a delete and replace. And then we /copy into that table from our CSV, and we tell the program that it is a CSV with a header row and blanks to be treated as nulls. Now, this line of code should all be on a single line. I have broken it up onto multiple lines so you can read it, but it has to be on a single line. After /copy, we create the indexes, and then we commit. So it's a really great way of writing to the database. /copy is really incredibly fast. When I call psql, I will not be able to pass in a password. So I need to provide that some other way. And I do that by storing all the database information, including our super secure password, in a config file called .pg_service.conf. We put all of our connection information inside of this file, and then when we call psql, it gets the password automatically. Super easy, really works really well. We then use process X to call psql, and when we do that, we say service equals medium data, so it knows to use this database information that we got from our service file. And we provide the file of instructions using -f. So all those steps were really great. They, a lot of them depend on each other. There could be a lot of complication. You want to make sure you don't duplicate. So it's important to use some sort of orchestration tool. You want to run those pieces smartly. You want to run them in the right order. You don't want to repeat steps. You don't want to have to worry about memory usage. Thankfully, we have targets. This puts everything together. It only runs steps that need to be reran. It doesn't waste any computation. It builds the DAG for us, the directed acyclic graph. It moves objects in and out of memory. It's very reproducible, and it's really changed my entire workflow. When you're using targets, your directory structure typically looks like this. You keep all your custom code, particularly your functions, inside the R folder, inside a file called functions.r. The naming is optional. Then you put all of your instructions inside of _targets.r. Everything goes inside of there. We'll look at that extensively. You set config and _targets.yaml. I put my database instructions inside copy to db.txt. You may or may not have that. I put my database files inside the database folder, and I have a Docker compose file for spinning up my container. Today, we are going to focus on targets.r. Inside there, you call library targets, and optionally target types, which gives you more advanced versions of targets. You source any code you need by sourcing, in this case, R functions. Then all of your commands, all of your steps go inside of a list, a plain old regular R list. Nice, super simple. So let's go back to the beginning where we started, and let's get the data. We use tar force to first check has the file changed, because we don't want to do this if the file hasn't changed. Tar force calls getBucketDF, which tells us if the file has changed. And if it has changed, our next step calls saveObject to download it. This target is a tar file because the outcome of this function is the name of a file on disk, and later steps will check if that file has changed, and tar file keeps track of that for us. We can visualize our DAG by calling tar viz network. Even though we only had 2 steps, it shows us 3 because tar force is actually 2 in 1. Typically, this visualization only will show the difference between outdated targets and up-to-date targets. But since I use tar force, that runs every time. So even though subsequent targets will be up to date, they will still be shown as outdated. And there's nothing we can do about that right now. Next, we need to split the data. Luckily, we wrote a function for that, and we can call that function. First, we split the data, and this time it's a tar target. It's a regular target because an R object is returned, a data frame of file names. And that feeds into our next target, which creates a mapping of input files and output files. When we visualize our DAG now, we see we have these extra steps, and the raw file step will only be called if the raw data step has changed. And that is only changed if we downloaded the data, which only happens if the file on S3 changes. To do our geofiltering, we need our map of our desired area, so we need to go download it. Again, we only want to download it if it has changed, so tar URL, given a URL on the internet, will keep track of that file on the internet and will let you know if that file has changed remotely. If it hasn't changed, you're good. If it has changed, the next step, tar target, which reads in this URL into SF, will be fired. So it's a great way of keeping track of files that are remote to you, so you don't have to worry about if they have changed. This part of the DAG has just two steps, checking if the file has changed on the internet and reading it into an SF object. You can see that these two steps are completely disconnected from the rest of the DAG. They're independent of each other because they don't have anything to do with each other for now. Because next we are going to do our spatial filtering, and that's going to combine our data and that map file. To do this, first we make a list of any existing filtered files in our output directory, and we delete them all. We don't want them around because we don't want overlap. We then take our data frame of input and output files and we map over that. See the pattern equals map? That allows us to iterate over one row at a time of this data frame to call our function remove points on each one individually. You can see here that this function depends upon our NYC map, our file name mapping, and in curly braces, we included remove filtered files because even though our function doesn't make use of it, I want this step to only occur after that removing data step has been successful. Looking at the DAG now, we see that removing the old files, making the input-output list, and the NYC map all feed into filtered files. Now, filtered files is a square, not a circle. Because rather than one step, it is a pattern of steps because it's going to be called for each of those rows in the data frame. So it's iterating over that pattern. With our data all processed, we can now do our aggregation-based filtering. This step uses tar change because our function, which calls arrow, doesn't actually refer to any of the previous steps. So I'm saying change equals the filtered file step. So if those files change, go ahead and run the step. The outcome of this step will be a file. So I say format equals file. And I tell it to load up the package arrow, because this way I don't need to specify the arrow namespace in that function. Targets and arrow don't really play nicely together, so you need to create and destroy the arrow object within a single target. And this gets even harder if you want to share schemas. Our DAG now shows the process files, which will only run if the filtered files have changed. Next up, we need to get the Docker container running. So I create a step called Docker up, and I actually have a list. Our step is a list. It has two parts to it, because your steps can be any valid R object. The first step calls Docker compose, like we saw earlier. This spins up the Docker container. But since calling Docker compose on a container that's already running gives a different message than on a new container, I also check when was this container created, and I will use that later to let us know if we should run other steps. This Docker up step is this one step by itself, disconnected from the rest of the DAG. With our database running, we can copy from the CSV to the table. So we want to call our process X to call pSQL. We need to remember to feed it our database information, which is medium data. This way it gets the password. And this step runs if either the Docker uptime changed or the process file itself changes. So that's why we use tar change and specify the change. Our DAG is now complete. We have all of our steps we need to take all laid out for us right here, and everything will happen nicely and automatically. And if we say targets only equals false, it also shows us our custom functions to make sure that We know if our function has changed, it changes the graph. So now we can run the whole pipeline, or at least whatever needs to be updated, by running one line of code. We run tar make and everything just runs, all nicely taken care of for us. If things don't need to be run, they don't need to be run. If they do, they do. But better yet, we can do this in parallel. That's really great. Let's take advantage of our split files. Remember, we had hundreds of them. And let's do each one individually in parallel. The first step to this is setting pattern equals map equals file name of mapping. This iterates over all those files, and since they are done independently, they can be done in parallel. Next up, in our arrow step, we need to be careful here. Arrow runs implicitly in parallel already, and we want to keep it in parallel. But we don't want a race condition with our other parallel steps. We want both. So we set deployment equals main for the arrow step, and that will run by itself in parallel, and then everything else will run in parallel also. We then make one change to our targets file. We say future plan of future multi-session, and I set 4 workers. I could have done more workers, but I set 4 workers. And now anything that can be done in parallel will. That means if you have 2 steps that have nothing to do with each other, they could run in parallel. If you have a step like our geoprocessing, which maps over a bunch of files, that will be done in parallel. If you have a step which uses a function like future map, that will be done in parallel. It's all nicely done for you. And the one more change we need to make is instead of calling tar make, we call tar make future. That's it. That runs everything in parallel, even across multiple machines. If you wanted to, you'd actually run tar make cluster MQ, but same idea. And this runs everything in parallel for you. You don't need to worry about it. You just go along from there and go on your smooth road. So we put together a lot of different tools. Let's see what we did. We used AWS for cloud storage. We used the command line for splitting and pre-processing files. We used data.table for reading and writing data, and then dplyr and pr for data manipulation. We used SF for geospatial filtering. We used arrow for operating on out-of-memory data, Postgres and PostGIS for holding the finished data, Docker for isolating the database, and targets for orchestrating everything. And this is great. This package put everything together, it built the DAG, it keeps track of what needs to be computed. It's easier than other orchestration tools, and it is all R-based. And that one package pretty much sums up the whole project, literally. It gives us the whole project right here in this one visualization, tells us everything that's happening, and does it all for you, allowing you to combine all these tools to help you work on data that would otherwise give you a bit of trouble. Thank you very much.